We've looked at the situation where an object is launched horizontally off of a cliff, and we solved it by treating the y direction to be just like a dropped ball, and we find the time of flight by using the acceleration and the displacement, and then multiply the time of flight by the x component of the velocity, which was the launch speed. So now we want to look at the situation where we launch the ball up at an angle, and it lands at the same height that it started. And once again, we can split the motion into the x direction and the y direction. So in the y direction, this is a problem that you already did, right? So we have our initial velocity in the y direction. We throw the ball up in the air, and we find that the time to the apex, so at the apex, the velocity in the y direction is 0. So that means if we know the initial velocity and the acceleration, we can find the time to the apex. Or if we want to know when the object hits the ground, we find when the final velocity is the negative of the initial velocity. That then gives us the time in the air. So to do this, we need the y component of the velocity, and then we just solve it doing the way we did before, using the vector components. We can also find the height, if we want, in the x direction. We do exactly what we did with the horizontal question. So there we find the x component of the velocity, and we multiply it by time. So we can do that because there is no acceleration in the x direction. So to do this, we need the x component of the velocity and the y component, and then we do that using our vector components. So the x component is the magnitude of the velocity times cosine theta, and the y value is the magnitude times the sine of theta. So if we look at our graph here, on the first spot, let's say our y component here is 20 meters per second going up. And then after 1 second, it's, let's say, 10 meters per second. It's 0 at 2 seconds. Then now, as it comes back down, it's negative 10 and negative 20. So it should make sense that the time up, and so those were the y components here. The x components are going to be constant the whole time. So that means that's just going to be the same no matter where it is. So yeah, so the point is we're doing just what we did before, but we have to keep track of what's happening in the x direction. We have to keep track of what's going in the y direction, and to solve them separately. All right, so let's do our problem. So we have a projectile that's launched at an angle of 30 degrees above horizontal. So something like this. So we're shooting it off, and so that angle here is 30 degrees. So it's sort of a larger x component than a y component. So first we want to know how long is the projectile in the air, so the hang time, and then we want to find the range, so how far the projectile traveled. Well, to start, we want to find out how long it is in the air, so we need to look at the y direction. That means we need the y component of the velocity. So to find that, we use our vector components, right? So that means we multiply the magnitude of the velocity by the sine of theta to get the y component. And so we do that. So our velocity is 100 times sine of 30. So that means it is 50 meters per second in the y direction. So the initial velocity is 50 meters per second in the y direction. Then how long does it take for its velocity to become negative 50 meters per second? Because we know that the speed in the y direction is the same when it lands as it is when it starts. So we set v final to be equal to v initial plus acceleration times time, and we solve for time. So our final velocity is negative 50 meters per second. 50 meters per second is our initial, and then our acceleration is negative 10. So we solve this, and we get that it took 10 seconds for our projectile to hit the ground. So yeah, you can probably do this one in your head. Every second, the velocity decreases by 10, so 50, 40, 30, and so on. So it'll take 10 seconds to get to negative 50. So now we want to find the range. To find that, we multiply the average velocity in the x direction times the time in the air. So that means we need the x component of the initial velocity. So to do that, out of order here, we need the x component. So that's going to be v times the cosine of theta. And to get that, we do 100. So the magnitude of the velocity times the cosine of 30 degrees. And that tells us that the x component of the velocity is 86.6 meters per second. We know the time is 10 seconds, so we then multiply the average velocity, which is the 86.6 in the x direction, times the 10 seconds, and so that tells us that we're going to get a range of 866 meters. So yes, that's all we're doing here. We're just combining two problems that we've done before and then putting them together. So I want you to look at this second problem here. So we have our golfer, and he has hit two balls that are exactly the same maximum height. So one travels a shorter distance and one travels a longer distance. We want to know which ball spent more time in the air. So let's focus on the y direction. The x direction doesn't really matter when we're talking about hang time. So let's say that we're standing way over here, so we're kind of at a pretty long distance, and really, right in the ball's shot straight towards us. So from our perspective, we really just see the ball go up and we see the ball go down. We can barely tell that it's moving towards us. So can we see a difference between these two shots? Remember, we don't know how hard these balls were hit, right? In fact, we can deduce that ball B was hit significantly harder than ball A. So we don't want to focus on that. That's more likely to confuse you. So the point is, if it reaches the same height, is the hang time, is it more, is it less, is it the same for the two balls that have the same maximum height? Okay, so you have some questions to do, and next we're going to look at some more complex projectile motion problems.